Hello, in this lecture we'll prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides of the triangle and its CVN. So here, this is triangle ABC, and the CVN is line segment AD. Again, the CVN is line segment AD in this triangle ABC. Again, so Stewart's theorem yields a relation between the lengths of the sides of the triangle to its CVN AD. So here, in this triangle ABC, side AC equals to B units in its length, side AB equals to C units in its length, and finally side BC equals to A units in its length, and the CVN AD equals to D units in its length, and here line segment BD equals to M units in its length, and finally line segment DC equals to N units in its length. And according to Stewart's theorem, the following equation is true: B squared times M plus C squared times N equals to A. Here we open the brackets. Inside the brackets we have D squared plus M times N. Again, B squared M plus C squared N equals to A, and inside the brackets we have D squared plus Mn. Okay, so we prove the first one in the first method. In the first method, we'll do a construction from the vertex A of triangle ABC. We'll draw perpendicular on side BC. Okay. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. We will define this line segment ED as X. We will define line segment AE as H. Here, line segment EC equals to X plus N, so I write it down. And here, line segment AE. From the drawing, it is very easy to see. Here, that line segment BE, this line segment BE, this line segment BE equals to BD minus ED. Okay, BE equals to BD minus ED. BE equals to BD minus ED. So BE, this line segment BE equals to BD equals to M units, as you can see here, BD equals to M units, so we substitute BD by M minus EX. According to our definition, line segment ED, again BE equals to BD minus ED. And line segment ED equals to X. So we substitute line segment ED by X. In conclusion, we found out that line segment BE, this line segment BE equals to M minus X. Okay, I repeat again that line segment BD equals to M units in select, and line segment DC equals to N units in select. Okay. In the next step, we'll implement Pythagoras theorem on the right triangle, triangle AED. So we'll implement Pythagoras theorem in the right green triangle, triangle AED. So in the right green triangle, triangle AED, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right green triangle, triangle AED, the hypotenuse is AD, and therefore the square of the hypotenuse is AD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE squared plus ED squared. Repeat again. In the right green triangle, triangle AED, according to the Pythagoras theorem, we get that AD square equals to AE square plus ED square. Okay, so AD equals to D units in its length, so we substitute AD by D. So if AD equals to D, then AD square is D square, and it is equals to AE square. AE equals to H units according to our definition, therefore AE square is H square. Plus ED square. ED equals to X according to our definition, therefore ED square equals to X square. So in conclusion, we found out that in the right green triangle AED, D square equals to H square plus D square equals to H square plus X square. Okay. In the next step, we'll focus on the right triangle, triangle AEC, this right triangle AEC, and we will implement the Pythagoras theorem in this right triangle, triangle AEC. This will be question number 1. In the right triangle, triangle AEC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AE square plus EC square. And we already found out that EC equals to x plus n. EC equals to x plus n. Yeah, I can write down that EC equals to x plus n. So if we found out that in the right triangle AC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. Okay. So according to equation number 1, here AC equals to B units, therefore AC square is B square, and it is equals to AE square. AE is edge, therefore AE square is edge square, plus EC square. Here EC equals to x plus n, therefore EC square equals to x plus n square. So I conclude found out that according to equation number 1, b square equals to h square plus x plus n square. Here we'll open the brackets on this side of equation number 1, and we'll get that according to equation number 1, b square equals to h square plus x plus n square. X plus n square equals to x square plus n square plus 2 times x times n. Okay. Yeah. According to equation number 1, we found out that b square equals to h square plus x square plus n square plus 2 times xn. Here we have h square plus x square, and we already found out that h square plus x square equals to d square. So we can substitute h square plus x square in this equation number 1 by d square. So we'll do it now, and we'll get that according to equation number 1, b square equals to h square plus x square is d square plus n square plus 2xn. So we found out that according to equation number 1, in conclusion, b square equals to d square plus n square plus 2 times xn. In the next step, we will implement the Pythagoras theorem on the right triangle ABE. This right triangle ABE. Repeat again. We'll implement the Pythagoras theorem on this green, on this pink right triangle ABE. So in the pink triangle ABE, according to the Pythagoras theorem, this will be equation number 2. So according to the Pythagoras theorem, in the right pink triangle ABE, AB square equals to BE square plus AE square. Repeat again. In the right periodic triangle ABE, according to the Pythagoras theorem, AB square equals to BE square plus AE square. This is the question number 2. Okay, so AB equals to C, therefore AB square is C square, and it is equals to BE square. We already found out that BE equals to M minus X. Here BE equals to M minus X. Therefore we substitute BE by M minus X. So if BE equals to M minus X, it means that BE square is M minus X square. So we substitute BE square by M minus X square plus AE square. A equals to H, therefore AE square equals to H square. In conclusion, we found out that according to equation number 2, in the right periodic triangle ABE, C square equals to M minus X square plus H square. Here we'll open the brackets on this side of equation number 2, and we get that according to equation number 2, C square equals to M minus X square equals to, according to the algebraic identity, that A minus B square equals to A square plus B square minus 2 times AB, we'll get that M minus X square equals to M square plus X square minus 2 times mx plus H square. So in this equation, equation number 2, we have H square plus X square. And we already found out that H square plus X square equals to D square. So we substitute H square plus H square in this equation, equation number 2, by D square. So we do it now, and we get that according to this equation, equation number 2, C square equals to M square minus 2mx, and X square plus H square equals to D square. So it is plus D square. So in conclusion, we found out that according to equation number 2, C square equals to M square minus 2 times mx plus D square. And according to equation number 1, we have already found out that B square equals to D square plus N square plus 2 times Nx. In the next step, we'll create equation number 3. And equation number 3 will be created by multiplying equation number 1 by m. Then we will multiply equation number 2 by n, and then we will add the two equations with each other, and this will be equation number 3. Okay? So, first of all, we will multiply the right side of equation number 1 by m, and then the right side of equation number 2 by n, and then it must be equal to the multiplication of the left side of equation number 1 by m, and then the multiplication of the left side of equation number 2 by n, and then we'll add the two expressions with each other, and this will give us equation number 3. So we'll multiply the right side of equation number 1 by m, so it is m. In the right side of equation number 1 we have d squared plus n squared plus 2nx, and then we will multiply the right side of equation number 2 by n, so it is plus n this is the right side of equation number 2, so it is n times m squared minus 2mx plus d squared, and it must be equal to the multiplication of the left side of equation number 1 by m, so it is m. In the left side of equation number 1 we have b squared, so in total it is mb squared, plus the multiplication of the left side of equation number 2 by n, so in the left side of equation number 2 we have c squared, so it is n times c squared. Okay, so this is equation number 3. We will open the brackets on both sides of this equation, equation number 3, and we will get that according to equation number 3 we have here m times d squared is md squared plus mn squared plus 2 times mnx. So we open the brackets here, plus here we'll open the brackets, n times m squared is nm squared plus n times minus 2mx is minus 2mnx. And finally n times d squared is nd squared. N times d squared is nd squared. So this plus nd squared. And it must be equal to, in the other side of equation number 3 we have mb squared plus nc squared. So actually this is equation number 3 after we open the brackets on the right side. On the in the left side of this equation, equation number 3, we have plus 2mnx minus 2mnx, it is 0, so those two expressions will get cancelled because they are equal to each other, and they are in the opposite, one is plus and one is minus, and In the next step, we will take out a common factor of d square from this expression and from this expression. So d square was taken as a common factor from md square. So inside the brackets we left with m plus we have this expression n d square. We took d square as a common factor. So what is left is n. So inside the brackets we will have n plus in the next step we take a common factor of m times n from this expression and from this expression also. So what is left from n and m square after we took from it mn as a common factor? What is left is actually m plus what is left from mn square after we took from it mn as a common factor. What is left is actually n. So inside the brackets we will have n, and it is equals to b square m plus c square n. Here we take out m plus n as a common factor from those two expressions. So m plus n is taken as a common factor. What is left from this expression after we took from it m plus n as a common factor? What is left is actually d square plus what is left from this expression after we took from it m plus n as a common factor. What is left is actually m times n, and this is equals to b square m plus c square n. M plus n equals to a here. Side BC of triangle ABC is equals to a unit in its length. BC equals to a unit in its length, and BC also equals to BD plus DC. Again, BC equals to BD plus DC. BD equals to m units, and DC equals to n units. In conclusion, BC equals to m plus n, and BC also equals to a, so m plus n equals to a. So we will substitute m plus n in equation number 3, this equation number 3, by a. And we'll get that according to equation number 3, m plus n is a, so here a. Inside the brackets we have d square plus mn. In the other side of equation number 3 we have b square m plus c square n. And this is exactly Stewart's theorem. Okay, so we actually proved Stewart's theorem according to the first method. In the next step I will present to you the proof of Stewart's theorem according to the second method. In the second method, we'll define this angle ADB as theta. And because of the fact that side BC is a straight line, and we know that the sum of the angles on one side of a straight line is equal to 180 degrees, so if this angle equals to theta, so if we focus on the upper side of the straight line BC at point D, here the sum of the angles must be equal to 180 degrees. So this angle equals to theta plus the missing angle, in total they must be equal to 180 degrees. So the missing angle must be equal to 180 degrees minus theta. Okay, 180 degrees minus theta plus theta is 180 degrees, exactly according to rule number 1. Okay. In the next step, we will implement the law of cosines in the green triangle, triangle ABD. This green triangle. And then we'll implement it on the pink triangle, triangle ADC. I will remind you what is the law of cosines. First of all, the law of cosines is true in any triangle. So the triangle that I will draw here could be any triangle. This is triangle ABC. That could be any triangle. We know that the length of side AB of triangle ABC is equal to A units, side AC equals to B units in its length, side BC equals to C units in its length, and angle BAC, this angle equals to theta. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B cosine theta. Okay. Here we will add 2 times AB cosine theta to this equation, then we will subtract from this equation C squared, and then we will divide it by 2 times AB, and we will get that cosine theta equals to A squared plus B squared minus C squared over 2 times AB. Okay. This is true in any triangle, so we will implement the law of cosines in the green triangle, triangle ABD. So in the green triangle, triangle ABD, according to the law of cosines, this will be equation number 1. So according to the law of cosines, in the green triangle, triangle ABD, we'll get that cosine theta equals to m squared plus d squared minus c squared over 2 times dm, or md, 2 times md. Okay, so here, equation number 1 is the implementation of the law of cosines in the green triangle, triangle ABD. Cosine theta equals to m squared plus d squared minus c squared over 2 times md. In the next step, we'll implement the law of cosines in the pink triangle, triangle ADC. This will be equation number 2. Triangle ADC. The pink triangle. So according to the law of cosines in the pink triangle, triangle ADC, we'll get that cosine 180 degrees minus theta equals to d squared plus n squared minus 2 times dn, d squared plus n squared minus b squared over 2 times dn. Repeat again. According to the law of cosines in the pink triangle, triangle ADC, cosine theta equals to 180 degrees, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times dn. According to the trigonometric identity, that cosine 180 degrees minus theta equals to minus cosine theta. So we'll use this trigonometric identity and we'll substitute cosine 180 degrees minus theta in this equation, equation number 2 by minus cosine theta. We'll do it now and we'll get that according to equation number 2, cosine 180 degrees minus theta is minus cosine theta. And it is equals to d squared plus n squared minus b squared over 2 times dn. And according to equation number 1, cosine theta equals to m squared plus d squared minus c squared over 2 times md. Here we will multiply this equation, equation number 1 by minus 1, and we will get that cosine theta times minus 1 is minus cosine theta, and it is equal, we multiply the other side also of this equation, equation number 1 by minus 1, so we'll have here minus, inside the brackets we will have m squared plus d squared minus c squared over 2 times md. Okay, we have 2 different expressions for minus cosine theta. In the next step, we will create equation number 3 that states that minus cosine theta, according to equation number 1, must be equal to minus cosine theta according to equation number 2. Okay? So minus cosine theta according to equation number 1 is equal to minus m squared plus d squared minus c squared over 2 times md, and it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times dn. In the next step, we multiply this equation number 3 by 2d, and we will get here, we have here minus 2d over 2d is 1, so in the denominator we left only with m, and the numerator didn't change. So in this side of equation number 3 we have minus m squared plus d squared minus c squared over m, and it is equals to, we multiplied this equation, this side of the equation also by 2d, of course. So 2d over 2d is 1, so 2d will get cancelled, and we left only with n in the denominator, and the numerator didn't change. So in total we get that in the right side of equation number 3 we have d squared plus n squared minus b squared over n. Okay, in the next step we'll cross multiply this equation number 3, and we'll get that according to equation number 3 here we have minus n, inside the brackets we have m squared plus d squared minus c squared, and it is equals to m, inside the brackets we have d squared plus n squared minus b squared. So this is equation number 3 after we cross multiply it. In the next step we will open the brackets on both sides of this equation number 3, and we will get that minus nm squared minus nd squared plus minus times minus is plus nc squared equals to, here we'll open the brackets here, so it is md squared plus mn squared plus minus mb squared minus mb squared. M times minus b squared is minus mb squared. In the next step, we will add to this equation number 3, nm squared, and then we will add to it nd squared, and then we will subtract from it nc squared. Okay? And we will get, so in this side of the equation, m squared minus nm squared is 0, and d squared minus nd squared is 0, and nc squared minus nc squared is 0. So in this side of equation number 3, we left with nothing, it is 0. in the other side of equation number 3 we have already md squared plus mn squared minus mb squared. We added to this equation nm squared. We added also nd squared, and we subtracted nc squared. Okay. In the next step, we take out a common factor of this square from this expression and from this expression. So this square was taken out as a common factor. Inside the brackets we have here m, and from we took out this square as a common factor from this expression, so inside the brackets we left only with n. Plus we will take out m times n as a common factor from this expression and also from this expression. Okay. What left from n minus nm square after we took from it mn as a common factor? What is left is actually m, and what is left from mn square after we took from it mn as a common factor? What is left is actually n. And we have also here minus mb square minus nc square equals to 0. Is equals to 0. In the next step, we will add to this equation mb square and also nc square. And we get that according to equation number 3, d square m plus n plus mn m plus n. So we added to this equation mb square, mb square minus mb square is 0, so in the other side of the equation we have mb square plus nc square. nc square minus nc square is 0, so the other side of the equation we will have plus nc square. Okay. In the next step, we will take out m plus n as a common factor from those two expressions, and we'll get that according to this equation, equation number 3. So here m plus n was taken out as a common factor from those two expressions. So here inside the brackets we left with d squared, and from this equation we took out m plus n as a common factor. So what is left from this expression, we took from it m plus n as a common factor. What is left is actually m times n, and is equal to b square m plus c square n. I've already shown to you that in the first method that m plus n equals to a, so we substitute m plus n in this equation, equation number 3, by a, and finally we'll get that a times t square plus m times n equals to mb square plus nc square. And this is exactly Stewart's theorem. So we proved Stewart's theorem in both methods. In the next step, I'll summarize the lecture. We start with the first method, of course. So in this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides of the triangle to its median, to its CVN. I'll repeat again. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides of the triangle to its CVN. The CVN here is AD, and AD equals to the unit in its length. We know that side AC equals to the unit in its length, in this triangle ABC. Side AB equals to C units in its length. Side BC equals to A units in its length. Line segment BD equals to M units, and line segment DC equals to N units in its length. And we have to prove that this equation is true, that B square M plus C square N equals to A D square plus M times N. Okay? So, in order to prove Stewart's theorem according to the first method, we did a construction from point A, we drew perpendicular on BC. Again, from point A, we drew perpendicular on BC. Therefore, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. Then we implemented the Pythagoras theorem. Actually, we defined side A, line segment AE as edge. We defined line segment ED as X. Here EC equals to X plus N, as you can see from the drawing. And here BE, this line segment BE equals to BD minus ED. BD is M, ED is X, so in conclusion we found out that this line segment BE equals to M plus X units in its length. Okay, so we implemented the Pythagoras theorem on the main triangle, triangle AED. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle AED, it means that AD square equals to AE square plus ED square. Repeat again. The right triangle AD, right triangle, according to the Pythagoras theorem, AD square equals to AE square plus ED square. AD is D, AE is H, and ED is X. Okay, therefore it is equals to AD equals to D square, so and A equals to S, therefore A square is S square, and ED equals to X, therefore ED square equals to X square. So in conclusion, we found out that according to the Pythagoras theorem, D square equals to H square plus X square. Then we implemented the Pythagoras theorem on triangle AEC. On this triangle AEC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. Again, AC square equals to AE square plus EC square. Repeat again, in the right triangle AEC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. AC equals to B, therefore AC square is B square. AE equals to H, therefore AE square is H square. And finally, EC equals to X plus N, therefore EC square is X plus N square. So in conclusion, we found out that in the right triangle AC, AC square equals to AE square plus EC square, so B square equals to H square plus X plus N square. Okay, here we open the brackets in this side of equation number 1 and found out that B square equals to H square plus x squared plus 2 times xn. We already found out that h squared plus x squared equals to d squared, so we can substitute h squared plus x squared in this equation number 1, by d squared. We did it, and we found out that according to equation number 1, b squared equals to h squared plus x squared is d squared, plus n squared plus 2 times xn. Okay, and then we created equation number 2 by implementing the Pythagoras theorem of the pink right triangle, triangle ABE. On the pink right triangle, triangle ABE, according to the Pythagoras theorem, AB squared equals to AE squared plus EB squared. Again, AB squared equals to AE squared plus EB squared. I'll repeat again in the right triangle AB. AB squared equals to EB squared plus AE squared. AB equals to C. Therefore, AB squared is C squared. BE equals to m minus x, therefore BE squared is m minus x squared. And finally, AE equals to h, therefore A squared is h squared. So in conclusion, found out that according to equation number 2, c squared equals to m minus x squared plus h squared. We open the brackets on this side of equation number 2, and found out that c squared equals to m minus x squared equals to m squared plus x squared minus 2 times mx plus h squared. Again, x squared plus h squared equals to d squared according to this equation. So we substitute x squared plus h squared in this equation number 2, by d squared. And therefore, in this equation number 2, we get that c squared equals to m squared minus 2 times mx, and x squared plus h squared is d squared. Okay, so we found out that c squared equals to m squared minus 2 times mx plus d squared according to equation number 2, and we have already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times nx. In the next step, we created equation number 3. Equation number 3 was created by multiplying equation number 1 by n, then we multiplied equation number 2 by n, and then we added the two equations with each other. This created equation number 3. So we will multiply the right side of equation number 1 by n, then we multiply the right side of equation number 2 by n, and it must be equal to the multiplication of the left side of equation number 1 by n plus the multiplication of the left side of equation number 2 by n. Okay, so we started with the right side. We multiplied the right side of equation number 1 by n. So this is the right side, so it is m times d squared plus n squared plus 2 times nx plus the multiplication of the right side of equation number 2 by n. So it is n, and this is the right side. In the right side of equation number 2, we have m squared minus 2mx plus d squared. And it must be equal to the multiplication of the left side of equation number 1 by m. In the left side we have here b squared. So it is m times b squared plus the multiplication of the left side of equation number 2 by n. We have in equation number 2 we have in the left side c squared, so it is n times c squared. So this is equation number 3. Then we open the brackets in this side of equation number 3, and we found out that it is md squared plus mn squared plus 2 times mnx plus m squared minus 2 times mnx plus nd squared. And it is equal to mb squared plus nc squared. So this is actually equation number 3 after we open the brackets. 2mnx minus 2mnx equals to 0, so those two expressions will get cancelled. Then we took out a common factor. We took out a common factor d squared from this expression and from this expression. Okay, so inside the brackets we left with m plus n. Then we took out a common factor mn from this expression and from this expression, and therefore inside the brackets we left with m plus n, and it is equals to b square m plus c square n. Then we took out a common factor of m plus n from those two expressions. So inside the brackets we have d squared plus mn, and it is equals to b square m plus c square n. We can see here that m plus n equals to a. M plus n equals to a. So substitute m plus n, this equation are referred by a, and we got that here m plus n is a, so it is a times d squared plus mn equals to b squared m plus c squared n. This is actually the proof of Stewart's theorem, or the proof of the equation of Stewart's theorem. Okay, so we finished with the first method. Then I presented to you the second method. In the second method, we defined angle ADB as theta. We defined the adjacent angle as minus 180 degrees minus theta, according to the rule that the sum of the angles on one side of the triangle, on one side of the triangle is equal to 180 degrees. This angle must be equal to 180 degrees minus theta. And then we implemented the law of cosines in the green triangle and then in the pink triangle. What is the law of cosines? The law of cosines is true in any triangle. So this triangle ABC could be any triangle. The length of side AB is A, the length of side AC is B, and the length of side BC is C, and this angle BAC equals to theta. Then according to the law of cosines, C squared equals to A squared plus B squared minus 2 times AB times cosine theta. With a couple of operations, it is very easy to see, to arrive to this equation, that from this equation to this equation, that cosine theta equals to a squared plus b squared minus c squared over 2 times ab. In the next step, we implemented the law of cosines, this law, in the green triangle. So in the green triangle, triangle ABD, according to the law of cosines, we get that cosine theta equals to d squared plus m squared minus c squared over 2 times dm. Repeat again. Cosine theta equals to m squared plus d squared minus c squared over 2 times dm or md. Okay, then we implemented the law of cosines in the pink triangle, triangle ADC. In this pink triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times nd. Repeat again, according to the law of cosines in the pink triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times dn. Then we have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. According to this trigonometric identity, we can substitute cosine 180 degrees minus theta by minus cosine theta. We did it, and we got that according to equation number 2, minus cosine theta equals to d squared plus n squared minus b squared over 2 times dn. Then we multiplied this equation number 1 by minus 1. Cosine theta times minus 1 is of course minus cosine theta. Then we multiplied also this side of the equation by minus 1. So we will have minus 1, inside the brackets we will have m squared plus d squared minus c square over 2 times md. Then we created equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 1 is m squared plus d squared minus c squared over 2 times md. It must be equal to minus cosine theta according to equation number 2, and minus cosine theta according to equation number 2 is d squared plus n squared minus b squared over 2 times dn. Here we multiply this equation number 3 by 2d. So here 2d over 2d is 1, so 2d will get cancelled. So in the denominator we left only with m. The numerator didn't change, so it is exactly the same. Minus m squared plus d squared minus c squared. Then we multiplied this side also of equation number 3. This equation number 3 by 2d. 2d over 2d is 1, so 2d will get cancelled. So in the denominator we left only with m. The numerator didn't change. First it is d squared plus n squared minus b squared over n. Then we cross multiplied this equation number 3, and found out that according to this equation number 3, minus m squared plus d squared minus c squared equals to m. Inside the brackets we have d squared plus n squared minus b squared. Here we open the brackets on both sides of this equation number 3, and found out that according to equation number 3, we have here minus nm squared, minus n d squared, minus and minus is plus, so it is plus nc squared. We opened the brackets also here, so it is md squared plus mn squared minus md squared. Minus mb squared. So here we added to this equation nm squared. Nm squared minus nm squared is 0. We added also nd squared, so nd squared minus nd squared is 0. We subtracted from this equation number 3, nc squared. So nc squared minus nc squared is 0. So in this side of the equation we left with 0, nothing. On the other side of the equation we have already have here md squared plus mn squared plus mb squared, and we have to add to this equation nm squared plus nd squared, and we have to subtract from it nc squared. So we got this expression. In the next step we took out this square as a common factor from this expression and from this expression. So inside the brackets we left with m plus n. Then we took we took out nm as a common factor from this expression and from this expression. So inside the brackets we left with n plus m, and it is minus mb squared minus nc squared, that is equal to 0. In the next step we added mb squared and nc squared to this equation number 3. So we have here this square m plus n plus mn m plus n equals to mb squared plus nc squared. Then we took out m plus n as a common factor from those two expressions. So inside the brackets we left with d squared plus mn. Here inside the brackets we left with d squared plus mn, and it is equal to mb squared plus nc squared. N plus m is a. I've already shown to you that in the first method that m plus n is a, so we substitute n plus m by a, and finally we found out that here m plus n is a, so it is in total a d squared plus mn, that is equals to mb squared plus nc squared, and this is exactly Stewart's theorem. Okay, so we succeeded to prove Stewart's theorem in two different methods. Okay, thank you very much.